the first semester, first year of med school is like biochemistry and molecular biology, so it's a good idea to have it even if it's not required. Anyway, the more salient piece of information here is that that section is going to be offered in Dundee, Scotland. I emailed everybody flyer for that. Heather Comstock will be teaching it. We've taught biochem in Dundee a couple of times, and it gets really good reviews. It's not London, right? It's not a metropolis, but it's a really nice university town. Weather's nice in Scotland that time of year. So anyway, if you're interested in studying abroad and you're thinking about studying abroad in the summer, check out that class. Questions up to that point? Okay, so let's dive in on chapter 20. This chapter concerns carboxylic acids, which you should know, and their derivatives. You know some of these, but you might not know they are derivatives. So first of all, let's just kind of the simplest, acetic acid. The nomenclature for carboxylic acid is sort of name it like an alkane and then just say acid at the end, right? So for the free CO2H, that's what you get. pKa of acetic acid is about 4.8. Again, you guys do not have to memorize pKa numbers. You should memorize pKa numbers, but you should know ballpark figures, and you should be able to, like, you should have a few of these compounds in your head. So if you need to compare them, which you will, that you can, compare them. So if you know that carboxylic acids as a group are going to mostly fall between 3 and 5 pKa. All right, I'm going to show you one here in a bit that is below that. Not many are going to be higher than that. So they're reasonably strong acids, and in a biological setting, they tend to be the strongest acids. Right. So in the lab, we can pull out a jug of sulfuric acid, and that's our strong acid. Right. It's not going to surprise any of you that you can't have sulfuric acid floating through your blood vessels, right? So the strongest acids in a biological setting are a lot milder than the strongest acids in a lab setting. Same is true for bases. So in a biological setting, carboxylic acids tend to be the strongest acids. Amines tend to be the strongest bases. Chapter 21 is amines. We'll do that next. So let's before we get into like more complicated chemistry, let's think about you know what? Hydroxide is too easy. Let's think about amines. That's trimethylamine, again, hinting at chapter 21. All right, so amines also get named kind of simply. It's just like name all the things on the nitrogen and then say amine. So draw the product of this acid-base reaction. Give you a couple of minutes for that. Draw the product and tell me which side is big. In your way. Okay, so carboxylic acids, it's an acid, it's a Bronsted acid. Bronsted acids donate a proton. Proton's going to be the one on oxygen, right? We've also got 3 protons on this carbon. Chapter 22, looking ahead, we're going to look at the chemistry of protons on carbons bonded to carbonyls. Okay, so the proton bonded to this oxygen, which is bonded to a carbonyl, that carbonyl's electron withdrawing, it will stay, an electron withdrawing group would stabilize a negative charge on the oxygen. would pull electron density out of this OH bond. So the carbonyl has the effect of making this H a lot more acidic than you'd otherwise expect. It has the same effect on the CH protons. Right? A CH proton, you should think at this point, is not terribly acidic. If you put a carbonyl next to the CH, it becomes a lot more acidic. Right? It's still not acidic. But if you have a strong enough base, you can pull it off. All right, in this case, OH proton is acidic. Over here, if this is going to be the base, you got to figure out what the basic atom is. H's, C's that are neutral, don't have electrons, those are not going to be bases. And nitrogen with a lone pair will be basic. So our mechanism here, I didn't ask for a mechanism, but let's do it for kicks. Nitrogen has electrons, the arrow is always going to start with electrons. Nitrogen grabs the partial positive proton, the OH electrons, right? So again, this arrow gets drawn from the bond. These two electrons are making a bond to the H, so the arrow goes to the atom. Here, the H is losing electrons, so the arrow doesn't go from the H, the arrow goes from the electrons. We're charting what the electrons do. And that's going to give us right? So neutral oxygen gains some electrons, it's going to become negative. That nitrogen gets an H, loses the lone pair. Nitrogen with 4 bonds has a formal positive charge, right? If this nitrogen gives away electrons, it's going to become positive, more positive. So that would be the product of the acid-base reaction. Which side's favored? What does your gut say? It's a good gut.
You read it on that.
Why?
Because the charge.
Right. So people typically, so that's wrong. So your gut is good. Like you guys have been taught, and like I said, this is one of those things where, by and large, like if you're forced to guess only based on charges, having everything be neutral is probably the way to bet. But it's like a 60-40, 70-30 sort of thing, not a 99-1. It's not weird at all that the right side of this equation is favored. All right, even though that side's got charges. So think about what we're trying to do. Those charges are bookkeeping. What we're trying to do is stabilize electrons. Here on the left, the electrons that change, we've got a lone pair that is localized on a nitrogen. On the right, if we think about, right, let's put in just like not all the lone pairs, let's just put in the 2 that wind up over here. That lone pair now is delocalized on an oxygen. So that, if you think about it from that perspective, the right side being favored, that makes some sense. And it turns out that the pKa of trimethyl ammonium is like 9.9. And as a group, quaternary ammonium cations have a pKa of something like 8 to 11. Make sense? Makes sense. I'm asking you if it makes sense. I'm telling you a fact, and I'm asking you if it makes sense. It doesn't matter if it makes sense. pKa of ammonium cations, 8 to 11. Okay, so look at this. As a group, carboxylic acids have a pKa of 3 to 5. As a group, quaternary ammonium salts have a pKa of 8 to 11. What this says is if you have an acid-base reaction between a neutral amine and a carboxylic acid, the products of that will be favored by something like 4 to 8 orders of magnitude. And so in the body, like I said, carboxylic acids are going to be the strongest acids in your body. Amines are going to be the strongest bases. If you have an amine and an amine and a carboxylic acid in your blood system, they're not going to exist as a carboxylic acid and an amine. They're going to exist as a carboxylate and a protonated ammonium salt. Okay. Like I said, this is one of those reactions that, like, how much of organic chemistry do you need to know to be a doctor or a biologist? Not nearly as much as we teach. Right? We're sort of teaching for growth. Hopefully, if you go off and you're a doctor and you know more than just the bare bones basics to do your job, you improve the field. This is a bare bones basic thing you need if you work in the biological sciences, anywhere there's, you know, organic tissue. Carboxylic acid and an amine favor the acid-base reaction products are favored. Okay, that is just something you should know. Like I said, it's not a bad idea to have the pKa's in mind. pKa of a carboxylic acid 3 to 5, pKa of an ammonium cation 8 to 11. And I want to make another point. This will segue us into the next. What is that functional group? And is it a base? Did you have it? No? You too, I saw your mouths move, but I couldn't. It's an amide. I don't read lips well, but that's what I thought you said. So I was trying to. This is an amide, an amide, an amide. Here's the. These are close. These are close not just in. They're not close just in how they sound. So if you're talking fast in a loud room, it might be hard to hear this. They look similar, right? We got a nitrogen bonded to 3 things. We got a nitrogen bonded to 3 things. That nitrogen has a lone pair. You would expect that it's going to be similar. Similar name, similar structure, and yet the 2 groups are completely unalike. All right. So this amine up here is a pretty strong base. Like I said, strongest base you're going to find in biological tissue. Down here, it's not very basic. The amide is not very basic. So protonate this. Let's do this reaction. Protonate the amide. Think carefully. It's not all that straightforward. How many of you have put the proton on the oxygen? Congratulations, where it goes. If you put it on the nitrogen, I congratulate you on your pattern recognition, right? I spent like 10 minutes drilling you amines, protonate the nitrogen, it's a really strong base. This nitrogen has an electron withdrawing group next to it, bonded to it. All right, so you can draw a resonance structure that looks like this. Note the double barbed resonance arrow. And we've talked about this a little bit. This resonance structure that I've drawn down below, it has, this isn't, so amide bonds are also called peptide bonds because this is what makes up proteins. This is what links amino acids together. The amine group of an amino acid bonds through an amide bond to the carboxylic acid, the carbonyl of a carboxylic acid group. And that gets us a string of amino acids that makes up a lot of this. All right. That amide bond, there's significant carbon-nitrogen double bond character there, to the point that if you take an NMR, the compound I've drawn, you'll get a different signal for each method. You'll get 2 singlets close to each other, but separated a little bit. Right? There's not very fast rotation around that carbon-nitrogen bond. It also ties up this lone pair on nitrogen. That lone pair on nitrogen is interacting with the carbonyl, right? And so it makes the oxygen more basic and it makes the nitrogen a lot less basic. If I protonate the nitrogen, there's no way for me to delocalize that charge anywhere. That positive charge is localized on the nitrogen. Moreover, it's next to a partial positive atom. If I protonate the oxygen, right, then I could actually delocalize the electrons down here. I can have, but well, let me draw a product. How about that? Stop just waving my hands around. So if I protonate the oxygen, oxygen grabs the proton. If I put this here, that positive charge ends up delocalized. Right, so the resulting cation is a lot more stable if you protonate the oxygen than the nitrogen. Yes.
Could you first draw the same structure and
Absolutely. Yeah. So this comes up on pretty much any time you have an intermediate in a mechanism you're drawing, right? So let's say some far-fetched thing happens and I ask you to draw a mechanism. If there's an intermediate there that's got a resonance structure, you can either include the arrows that would make the resonance structure in the step, or you can explicitly kind of tell me these two are resonance structures, I'm going from here. If you do that, make sure you don't call it an equilibrium, right? Two resonance structures are just two different ways of drawing the same thing. So you want an arrow that's a single lined arrow that's got a double barb on both ends. That tells me you know these two are resonance structures. Here, a single barb arrow going one way, or really better here would be two-way street, right? That tells me these are two different molecules that can go back and forth. And a lot of you are probably like, that is, like you might think those are the same thing. Two different ways of drawing the same molecule, or two different molecules that just go back and forth. Those are two different things, but it's a subtle difference. And sort of exhort all of you to work on that. Like I promise, even if you got it down and you know what I want to see, you know how to make me happy, deep in your heart, you probably still don't fully get the implications of all that. I know I didn't for a very long time again. Okay, so let's get on with chapter 20. They're derivatives, carboxylic acid derivatives. An amide is a carboxylic acid derivative. And this is, so what I've just drawn here, anytime we protonate a carboxylic acid derivative, we're going to protonate the oxygen. Not the thing that's single bond. We're going to protonate the carbonyl oxygen. Moreover, a carboxylic acid derivative look like this. And so a carboxylic acid derivative is going to have a carbonyl directly bonded to an atom that is not a carbon or a hydrogen. If you have a carbonyl only bonded to carbons, that's a ketone. If you have a carbonyl bonded to a hydrogen and a carbon, or two hydrogens, that's an aldehyde. Chapter 19. So if you have a carbonyl, it can be bonded to one carbon, but if there is another atom bonded to that carbonyl that is not a carbon or a hydrogen, it is a carboxylic acid derivative. When you protonate it, you protonate the oxygen. What did I want to say? Nope. And so a lot of what this chapter is involved with is ways to turn a carboxylic acid into a derivative. And also, hydrolyzing carboxylic acid derivatives back to the carboxylic acid. This should look fairly similar. Like we did this with acetals. So we could take either a ketone plus an alcohol. Right? So you can make an acetal from a ketone or an aldehyde by adding alcohol to it. That's going to be acid catalyzed. And then we can take this side. And if we take water and acid, we can go from the acetal back to the carbonate ketone or the aldehyde. This is also called hydrolysis. You're going to see that word quite a bit. A hydrolysis reaction, as opposed to a hydration reaction, which you guys saw in Orgo 1. A hydrolysis, you're going to break bonds, or you're going to cleave a molecule in multiple bits using water. So water will add to the molecule. You'll actually get water incorporation into the molecule, and you'll split stuff out. Make sense? Right in front of you, sorry. All right, so what are these carboxylic acid derivatives? My own pen, sorry. So, the aptly named acid chloride, right? So you replace the OH with a Cl. You guys actually know reactions that do this, right? You've seen reactions in chapter 12. We'll talk about these. Chapter 12, you turn an alcohol into an acid or into an alkyl chloride. You do that with SOCl2 or PCl5 or whatever, right? So you can do the same thing. If I take a carboxylic acid, treat it with SOCl2, I get the acid chloride. And hydrides. We have the carbonyl, an oxygen, and then another carbonyl. All right, we're going to make that by taking two equivalents of carboxylic acid, putting them together, and pulling water out of it. That's why it's called an anhydride. We remove water. So two carboxylic acids come together, we make this new molecule, and it loses water. Bioesters. You guys know esters at this point, or you should, hopefully. I've talked about them a lot. Hopefully you saw them in Orgo 1. If you haven't, now is the time to learn what an ester is. So a thioester is an ester. Okay, again, an ester is going to be a carbonyl bonded to an oxygen bonded to a carbon. So here, R cannot be H. R can be basically anything other than H. If it's H, it would be called a thioacid, and those also exist. Right? We replace the R in an ester with an S, it's a thio. And you're going to see this for a lot of sulfur names, where sulfur is right below oxygen. So we just sort of, got lazy about naming things. And we're like, what's the oxygen name? Just put thio in front of it. And so then we get esters. Right? So again, carbonyl, oxygen, carbon, anything over there. We have amides. Here now, for an amide, R1 and 2 can be H. And It's the only one for this, for which this is true. This is going to be an amide. Pretty close to this, we have the nitrile. Right, the nitrile is just a cyanide where the carbon is bonded to something. And if you look at this, this is the only one that looks really different, right? Like that's not a carbonyl anymore. That carbon has a triple bond to nitrogen. But if you think about the oxidation state, look at all of these, the carbonyl carbon in all of these derivatives. Acid chloride, 2 bonds to oxygen, 1 to chloride. That's 3 bonds to heteroatoms. Ester, 2 bonds to oxygen, 1 bond to oxygen, 3 bonds to heteroatoms. In the nitrile, 3 bonds to nitrogen. So that carbon is in the same oxidation state as a carboxylic acid or any of the derivatives. That would have been a shorter explanation of what a carboxylic acid derivative is. All right, a carboxylic acid derivative is a molecule where you've got a carbon in the same oxidation state as a carboxylic acid. And then I'm going to put this down at the bottom for now because it'll be important in a minute. Just going to redraw right down here at the bottom, a carboxylate or a carboxylic acid. And remember, come back over and look at this first thing we did, acid-base chemistry, right? The carboxylic acid proton can come on or off depending on the pH of the solution it's in, depending on what acids are present, what bases are present. So these are essentially, they're not the same molecule. It's a chemical reaction that go back and forth from carboxylate to carboxylic acid. Right? But I can do that just with an acid-base reaction. Adjust the pH and I can change one into the other. Question? All right, so, and I've already drawn this a little bit. Hopefully you put this on here. The acid derivatives are not equally stable. So acid chlorides hydrolyze a lot faster than do esters or amides. Remember, the hydrolysis is going back to the carboxylic acid. So from any of these down to the green ones, right? So the addition of water. Basically, if you have an acid chloride or really an acid anhydride, if I add water to those, I don't need to do anything else. I just put water there and they'll really quickly go to the carboxylic acid. And they'll liberate HCl or acetic acid or whatever the other carboxylic acid is. Okay, so basically acid chlorides and acid anhydrides, either one of them by themselves, add some water, open them up in air that's wet, they hydrolyze. Thioesters then are a little more stable. You can make thioesters, and in fact, we do this. There are thioesters in all of you right now. There's not really so many acid chlorides or acid anhydrides. There are a lot of phosphates. So you guys, ATP, you guys have heard of ATP, right? It's like a tennis league or something, I think, right? Some crap in biology, I don't know. ATP gets hydrolyzed to ADP, AMP. That's a hydrolysis, and that linkage is really an anhydride. It's a phosphorus anhydride. Phosphorus oxide, like a phosphorus carbonyl, oxygen, phosphorus carbon. Hydrolyzing that liberates energy and lets us live. Thioesters are used in protein synthesis. So they're enzymes. You may have heard of coenzyme A. Anybody heard of coenzyme A? Acetyl coenzyme A. Some biologists probably wrote that as a cartoon. That's a thioester. Right. And so it's a handy way. Thioesters are easy. The bond breaks pretty easily. Holds together in water. You can make it swim through water, but you can react it really easily when you need to. Right. So if I need to like shuttle a part to make a fatty acid, I can hook it to a sulfur. I can let this enzyme sort of carry it around a little bit, and then I can react it immediately when I need. Esters, we don't actually find a lot of esters biologically. I don't know why. Like asking biological why questions gets you to, eventually it leads you to God. And either anger or love. Like one of those two. I'm not telling you to be religious. I'm just saying, like, eventually you get to a question that you can't answer scientifically. Like, why did this molecule evolve? No idea. It just did. So deal with it. So esters you don't find much. And this may seem strange, and but it's a reason esters do hydrolyze pretty easily. At one time in human history, we used esters almost always smell really nice. So small molecule esters have a nice odor. And so people have used those for perfumes, right? Like back in the day when indoor plumbing wasn't a thing, you were in the fields and you're all day. That's right. The trouble with that is just sitting on your humid, moist body temperature body, esters will hydrolyze. Right? I don't know if you remember, I heard butyric acid at one point and told you it was the principal component of foot odor, which is true. Right? So if you put a butyrate ester on your body, it smells really nice, then it hydrolyzes and you smell like foot. Okay, so esters are no longer used for perfumes a lot, but the main point, I don't know if you see a main point here, the main point is if we were built primarily of esters, we would not last very long. Right? You go out in the rain, you dissolve. That is an evolutionary penalty. Dissolution of your body is bad. So we're built mainly of peptides. You gotta really want to hydrolyze an amide. Right? Refluxing 6 molar sulfuric acid, that sort of thing. Right? Amides hold together really well. We've evolved a lot of, I say we, nature has evolved a lot of enzymes whose only job it is to go hydrolyze an amide because it's hard. Right? So amides, if you want a carboxylic acid derivative to stick around, an amide is what you want. Esters are somewhere in between, like they're, having an ester, it's hard to hydrolyze it, but it's too hard to hydrolyze it to make it useful, but it's not hard enough to make like the thing made of an ester last a long time. Okay, so this also goes with I'm writing these two things, they're the same thing. The higher you are on this table, the faster you react with nucleophile. Yeah.
So like the X groups aren't derivatives, but they're better leading groups.
Yeah, good. I'm glad you recognized that. Basically up here at the top, the leading group is better. There are other derivatives, I'm not listing all of them. Like you could have an acid bromide or an acid iodide. Like you won't encounter a lot of acid bromides because they're too reactive. They react so fast, they'll blister your skin. I did that when I was an undergrad, it was fun. I've never liked gloves, you guys may have noticed. I don't like gloves, I don't like lab coats. So I went in the lab, I was doing research. My boss told me to go use this acid bromide, and I didn't wear gloves. And he laughed. So anhydrides, the leading group here, right, is this thing. So it's a carboxylate ion. Basically, leaving groups that are weaker bases are better leaving groups. The other thing they do is they're more electron withdrawing. So that chloride is withdrawing electron density from that carbon, right? This carbon has got more of a partial positive charge on it because it's bonded to a chlorine. The other thing is, I did this in class, carboxylic acid derivatives are more stable than ketones and aldehydes because of resonance, right? The X group is donating electrons into the carbonyl to stabilize, help stabilize. The chloride is going to donate electrons a lot worse than a nitrogen. And in fact, if you were to draw in reactions with aldehydes and ketones, they would be somewhere in here. Like aldehydes and ketones don't hydrolyze down to a carboxylic acid. but they do react with Grignard reagents. And if I take, all else being equal, if I take an aldehyde, an acid chloride, and an amide, and I react with Grignard reagent, the Grignard will react with the acid chloride before it reacts with the aldehyde. It's not a useful enough rate difference, if that makes sense. Like, it's a small rate difference. You can't really add to an acid chloride without adding to the aldehyde or ketone. And usually you can't even add to a ketone or an aldehyde without adding to the amide. I want you guys Grignard reagents aren't selective. They react with all the carbonates. Okay, I'm going to do one mechanism just to get you underway. And one reason I'm going to throw this up here. I'm going to put the functionality on this thing. So here would be the hydrolysis of an ester. You guys have already seen this, right? You know what I'm talking about. So in the next room, you should go look at that actually on your way out. Don't take any because it's not time to divvy it up yet. You guys all made soap, right? If you're in the lab, you made soap last week. And I said there aren't many esters in biology. Fats are esters. So anyway, that's another conversation. You guys did this reaction. You heated up a bunch of aqueous sodium hydroxide. You added it to fat, which is an ester, and you got a hydrolysis reaction. Notice here that I've drawn this as an O minus. Why have I drawn the carboxylic acid as an O minus? Right, so we're in base here, right? I've not said anything about adding an acid at the end of it. If I wanted to get benzoic acid instead of benzoate, at the end of this reaction, I could just drop in like concentrated sulfuric or hydrochloric acid. I'd protonate this thing, and in water, benzoic acid is insoluble and it would fall out of solution. So the other thing is, if you're wondering, the sodium comes along to counter that charge. So the product of this reaction would be sodium benzoate. You could do this with potassium hydroxide to get potassium benzoate. You could do it with lithium hydroxide and get lithium benzoate. You do the pattern, right? So here's the mechanism. Basic conditions, this is just like we did with ketones and aldehydes. What starts us off is the base. So with the carboxylic acid derivatives under acidic conditions, which we'll do on Monday, or you can look at over the weekend, right? You're going to protonate. What drives the nucleophile is water. Water's a crappy nucleophile. So you've got to protonate the carbonyl first. Strong acid protonates the carbonyl, then water can attack the carbonyl. Under basic conditions, leave the carbonyl alone, just attack it with hydroxide. So O minus attacks the carbonyl. We get the tetrahedral intermediate. Then what happens? Yeah, so charge is going to come down, the O minus is going to make remake the pi bond. And now at this point, it could kick the OH out. If it does that, you just go back to the starting point, right? This is an equilibrium. Hydroxide adds in, gets kicked out, adds back in. It's just insistent. Like something's going to have to drive this equilibrium. It can either be how stable the molecules are, or it can be another step at the end. In this case, it's that. So let's kick out what we want to be the leaving group, right? Ethoxide and hydroxide are roughly the same strength of base. So it's kind of 50-50 shot here, which one gets kicked out. It's just if hydroxide gets kicked out, we go back to the start and we just go to all of them. All right, so we kick out ethoxide. And this is where a lot of students will leave it. Right? They're like, look, I hydrolyzed the ester to a carboxylic acid. That's the whole point. I'm done. Let me go home. but you're not done. I've said this a lot, like, how do you know when a reaction is done? Well, you look at what's present in the mixture. All the reagents, the starting material, the intermediates, and you ask yourself, would any of these react with something else in the mixture? And in this case, yeah, ethoxide is a strong base. Carboxylic acid is a strong acid, so you get an acid-base reaction. And this is what drives the equilibrium in this case. Okay, so I'll draw this as an equilibrium, but it's a very unfavorable, it's a very favorable equilibrium for the products. All right, so this acid-base reaction, remember the pKa of benzoic acid is going to be like 4.5. pKa of the ethanol is 17 or 16 or something like that. So the weaker acid's always favored. Here, the difference in acidity is like 12 orders of magnitude to a trillion-fold. So the carboxylate is favored over the carboxylic acid by about a trillion. Right? That's how you use the pKa, log units. So again, hydrolysis, this works for all of these. I just did a basic hydrolysis of a carboxylic acid derivative. Hydroxide adds in tetrahedral intermediate, the O minus reforms the pi bond, kicks out the leaving group, whatever it is. It could be a chloride, could be a nitrogen, could be a sulfur, whatever. You get a carboxylic acid and something else. If that something else is a strong enough base, it takes the proton, you go up to the product. Right? That works for all of those. On Monday, I will do the acidic mechanism, but you should probably take a look at it, like in all seriousness, you should take a look at it over the weekend. Yeah.
Was the grain a product of the hydrolysis of acid chloride?
Yes. Yeah, of all of them. The green is the green. If we hydrolyze any of these, we get the green. Right? And the green is also part of the faster reaction with nucleophiles. Right? You could, in principle, add a nucleophile to a carboxylate anion. There are some that do that. But remember that carboxylate anion is negatively charged. The nucleophile's negative, so you've got to put two negative ions together. So it's got to be pretty strong. You can't add a nucleophile to the carboxylic acid. How come? Why can I not add a nucleophile to a carboxylic acid? Yes, I think that was. Any nucleophile strong enough to add to the carboxylic, the carbonyl is just going to take the proton. Any other questions before we launch into this? So, no? Yes? Questions? So there's no lab today if you're in my Wednesday lab, but if you do want to look at the soap, I want to look at the soap. I said this will be 30 minutes. I don't think there's a class in here. If you got to catch the bus, I understand. The other thing is, I absolutely do not want, I'm not trying to add stress to your life. Like, I actually kind of thought this would be a nice low-key way to see where you are. Based on emails I got from a few people, and I'm guessing some people felt this way and didn't email, like it seemed to do more. If these get to the back, slide over. I'm just wanting you and I to get a look at where you are. If you know you're behind, put your best answers down. I'll mark it up and tell you, like, no, you're doing this wrong in the mechanism. You like think about it. Like, if you're worried, feedback is always hard. Right? I hate feedback. I don't talk to humans at times because I don't like feedback. If you'd rather get feedback from me, like over fall break, saying, hey, this mechanism is wrong, you got full credit, than on exam 2, right? So put everything away, act like this is a test, do your best. I'll get a key up later today or tomorrow. Everybody got one? All right. And have a very nice fall break. Like, take some break. Don't work every minute. Do work some. Don't take 5 days off of the world.